imagine slapping V into B with the palm of your right hand. Okay? So that's three different things. Remember to slap V into B and not vice versa. So start with V, slap it into B. Make sure that you don't karate chop it. Okay? You have to do it with the palm. There's no back slaps either. Okay? And it has to be your right hand. Okay? So if you do that, you will get the force. Now the thing to remember is that V and B do not need to make a 90-degree angle to each other. That can make any angle between 0 and 180. Okay? You're entitled to throw a charge into a magnetic field however you like. So the velocity and magnetic field, this can be any angle from 0 up to 90, even to 180. But the force ends up being perpendicular to both of these. So the force is always 90 degrees to both the velocity and the magnetic field. If you want, another way to think of it is that the velocity vector and magnetic field vector form a plane, and the force is perpendicular to that entire plane. Okay? So remember that these need not be perpendicular, but the force ends up being perpendicular to both V and V. Okay? Or again, if you prefer, the force is perpendicular to the entire plane that V and V lie in. Okay? So, first of all, for those of you that are in or have taken Calc 3, that we purposely don't make that a prereq or co-req for this, because it is certainly possible to succeed in this class without it, but this should be looking extremely familiar. You guys that have seen Calc 3 at this point, does this remind you of anything where you have two vectors that go in, one vector that comes out that's perpendicular to both the other two? The cross product, that's right. So it's possible to bundle all this up into a very simple law with the cross product. F equals QV cross B. So in math class, if you're wondering what is the possible usage of a cross product, well, here's one that occurs in physics. Okay? So if that helps you in any way to connect this to something you may or may not have seen in math class, great. But since not everybody has seen the cross product yet, I will just mention it as kind of a side point for those of you that it might be helpful for. Okay? So hopefully in physics, you see the utility of some of these things. For instance, dot product, we've used that a lot more, right? Two vectors go in, one scalar leaves, right? So that produces a number. Examples of that, well, dot product, we can't get away without using it in physics, so we introduce it even in physics 1, right? Work, F dot S. Two vectors walk in, force and displacement, one scalar leaves, work. Okay. I'm not going to similarly introduce dot product simply because I think we can get away without it. Just remember, if you come in late, just try to go up the backside. It's like walking into a movie theater just late and just going like this across the screen. Okay. The big difference, of course, is with the cross product, two vectors go in, another vector leaves, a third vector leaves. Okay. By the way, I should mention that this is for a positive charge. Of course, the negative charge is the opposite. Everything that a positive charge does, the negative charge will experience the opposite. This hasn't changed. This is the same as with the electric field stuff. And so I'll give you two options for that. Option 1 is just to use the right-hand rule and reverse the answer. Okay? So whatever direction you get with the right-hand rule, just do that opposite direction of that is the force on a negative charge. So for instance, in my case right here, I can slap V into B, I get the forces up, then I remember it's a negative charge, so the force is actually down. Or the other option is to naturally make use or exploit what is going on with why you have to use the right hand rule in the first place. The reason why you have to use your right hand is because if you slap something into something, you get, of course, the wrong answer if you're using your left hand. Well, in this case, the flaw becomes the feature, okay? So for a negative charge, you can use the left hand rule. So again, if you slap something into something, you'll get opposite answers with your right and left hands. That's a bad thing. If you aren't paying attention to which hand you're using, you might get the wrong answer. But in the case of a negative charge, you might be actually exploiting that feature. Okay? Just don't, remember, this is an or, okay? This is not an and. The worst thing you can do is use the left hand rule and then reverse your answer, because you're going to get the same as you would have with the right hand rule. That's like a double negative, right? Okay, so it's an or, okay? And for those of you, again, that are comfortable with the cross product, notice here that Q has no absolute value sign. So if Q happens to be negative, it'll just reverse the answer for you. So it works out perfectly. So if everyone was comfortable with the cross product, we do this, but we have to have all this because we try to phrase everything without it, okay? So with that, let's just do some practice, okay? First things first, I actually gave you the answer for the force for 2 different scenarios last lecture, and I just kind of said we'll learn how to do this shortly, and I want to go back. I don't have it on the board anymore because that was last lecture. Let's just practice our slap rule. So here's V, here's B. We point our fingers along V, okay? Then we do the beauty queen handshake like this, because we want to make sure that we are ready to orient V and push V into the B with the palm of our right hand. So with the palm, okay? So we do the slap, force is in, okay? So let's try it again here. We point our fingers along V, and then we decide we need to orient our palm, and we point it toward B because we're going to slap V into B. It's a relatively short slap, it's less than 90 degrees, force is in, okay? And again, it should be no surprise that the force is in the same direction because, remember, ultimately, it's V perpendicular that causes there to be a force at all. And V perpendicular points exactly the same way as the previous case. It's just that it has another component that is useless for any kind of force. So this and this are exactly the same, so same deal. We should probably practice a long slap as well. So this angle between B and B is somewhere between 90 and 180. And we point our fingers along B, then we figure out how do we orient our palms so we can do a long slap, okay? And force is still in, okay? So common mistake is to slap it not again to B, but the opposite, or not, is to do this, right? Slap V into B. The problem is B isn't pointing this way, it's pointing this way, okay? So we slap V into B, we have to turn our palm around like that. If it helps, remember B is like this, so we're slapping long slap. And if we do that, we still get that the force is into the page. So all 3 of these particles would experience a force into the page. And again, I can point out that if I broke this velocity into components, the V perpendicular points the same way for that one as the other 2. The only thing that's actually changed is that V parallel, which is irrelevant, happens to point against the field instead of with the field. But remember, you don't get magnetic force because of V parallel. You get it only because of V perpendicular. And it's the same in all 3 of these cases. Okay? So that's the right-hand rule. The only issue I have with the diagrams that I drew on the page it gets me a chance to see the 90-degree slap, the short slap, and the long slap. But all of these feel a force into the page, so these particles will immediately curve into whatever the hallway is out here with the vending machines. Okay, we can't see them, okay, behind the wall. So rather, I want to draw an orientation where when it curves, it stays on the page, and we can sort of explore what the subsequent shape of the trajectory looks like. Okay, so for that, I'm going to need to switch it so the magnetic field is into the page. So again, let me take it as uniform throughout the region, so I don't have to draw it everywhere and just have a nice clean diagram that's not cluttered up by that written everywhere. And I'm going to go ahead and get the party started with a velocity that's like that. All right, so let's try it. So I get out my right hand, I do the V to Queen handshake, and I realize now my palm has to point into the page because I want to slap V into B. So V into B, force is to the left. So now this thing will curve. It curves to the left because it gets a force to the left. And we're keeping this trajectory on the page so we can continue to explore what happens from here. Okay? Now, again, if you don't see that, remember that this is what we have. Oh, these flags keep on falling off. I swear I'll get this fixed. Sorry about this. Okay? So we have the same exact thing that we've been doing. You just need to be able to visualize it in all sorts of different orientations. So what we basically have is a 90-degree slap, where we're slapping V into B to get F. The only difference in this case is that this thing, you have to visualize it like this, right? So we have that B points away from you, B is up, so we're doing this slap, right? So the force is to the left. You just have to be able to visualize this in all sorts of different orientations. Okay? It's the same exact thing, it just looks very different. And that's just because it's really hard to draw 3 dimensions into in a 2-dimensional surface. So you just have to do your best to visualize it. Let's re-examine what happens after this thing has curved and now is going to the, let's say, to the left. So we go ahead, we point our fingers along V, we put our palm into the page because we need to slap V into B, forces down. So this thing will not continue to the left, it'll get pulled downward. You can probably see where I'm going with this. What is the shape of this going to look like?
Projectile motion.
Circle. Circle, that's it. By the way, you have an advantage that I don't. I cannot manipulate the whiteboard, and so I have to get into these arthritic contortions to keep on doing my slap roll. You can just, if you don't like what position you're getting into and you're going to hurt your wrist, just rotate the paper on your desk, do the right hand rule, put down the answer, and rotate it back. Okay? So, if this whole whiteboard was on a swivel, here's what I'd do. I would go, grab it, go like this, and then this would look like this. So you already did it the first time, then you just rotate this till it looks the same. You rotate this so it goes back like that, and then you realize you're doing the same right-hand rule over and over. So this, just flip your page upside down. If you flip your page upside down, then this looks like this. You draw on the force, and then when you rotate it back, it looks like this. Always good to do the right-hand rule in place if you can, but you don't have to.
Looks like this and this.
So, we keep going. And just to complete the scenario, slap B into B, Okay, force is up. So, it curves the motion of the charged particle into a circle. So we'll find out the properties of that circle in just a moment, but I do want to point out one important thing. This might be a good juncture to point it out. Remember we said that the force always ends up being perpendicular to both other vectors. So this is always a 90-degree angle, and I can draw it here in all four cases. So the force is always perpendicular to the velocity. You can certainly see that. You might be more skeptical that the force is always perpendicular to the magnetic field, but I will point out that even as this force changes direction, it stays in the plane of the page. Well, B is perpendicular to the whole whiteboard. So the force is indeed always perpendicular to both B and B. That's your head check. If you don't get that result, you did the right-hand rule wrong somehow. In particular, I want to point out that this is always perpendicular to the motion. So the force will never help the particle. It'll never have a component with the velocity to speed it up. The force will never have a component against the velocity to slow it down. So the magnetic force cannot change the speed of a particle. Okay? The magnetic force is what we call a guiding force. It cannot change the speed of the particle. It can only deflect the motion. Obviously, something doesn't spontaneously go in a circle by itself. That's not allowed by Newton's first law. The magnetic force, what it does is it deflects this motion into a circle instead of allowing this thing to go in a straight line. So if this in the absence of any force, would go in a straight line, well, it doesn't do that. It gets curved into a circle. But remember that it is going just as fast later when it completes that circle, and of course keeps going around and around and around. It's going just as fast as the moment you threw it into the field. Because the magnetic field is guiding this particle onto a path, in this case a circle, that it wouldn't normally take, but it's not changing the speed. If we want to say it fancy-like, we say that the magnetic force can do no work, and therefore cannot affect the kinetic energy. That's just a fancy pants way of saying the same thing, right? Question?
So the particle has no acceleration?
Whoa, that's a loaded question. It's very much accelerating. It's just not speeding up. Can anyone tell me what I just said?
Is it because the acceleration's in a different direction, or like rotational acceleration of the velocity is going in a circle? I can't explain it all.
The component.
Centripetal acceleration.
Yeah.
Yes.
So acceleration is not just about changing speeds, it's also about
Correct.
changing direction. And this is obviously changing direction, right? So remember, and then you can correct your friends all the time that haven't taken physics, right? Okay? Things that accelerate your car: gas pedal, brake pedal, and steering wheel, right? You gotta broaden your mind about what the word acceleration is. It's not just about. Okay. So I won't tell Adam you said that. Okay. So the magnetic force is having an influence. It's a deflective influence. It's guiding the particle into a path, a circle that it wouldn't normally take. Okay. So this is a common theme, and we should probably take a moment to figure out what are the properties of this circle. Well, the magnetic force is providing the centripetal force, right? So I'm going to go ahead and put in my formula, QVB sine of theta. And then over here, mv squared over r. so what is the angle that the velocity and magnetic field make to each other? That need not be, that could be anywhere between 180 and 0, but what is it in this problem?
90?
It is actually 90. Even the whole time it's circling, at any moment the velocity, if it stays in the plane of the page, is perpendicular to the magnetic field, right? So this happens to be 90, and that's true for the entire entirety of the circlet. And sine of 90 is of course 1, which means that we get maximum force. So we get maximum deflective force because we threw the charge in to the field at 90 degrees and it stays 90 degrees to the field. Then we go ahead, we solve for the radius of the circle. And you get that. I'm sure you can do the one-line algebra it takes to get that, if you don't already see it. And I should mention that that's probably one of the more important formulas that you're going to want to have access to that is not, I repeat, not on the equation sheet. Okay? Yes, you can find the magnetic force law on the equation sheet. You can find the centripetal force formula on the equation sheet. It's on the last page of the Physics 1 stuff. I don't think it's a tall order to ask you to set the 2 equal and solve for r. Okay? So I don't want to just give you random formulas, and because the rule is that if I give it to you on the equation sheet, you can write it down without any justification, and I want you to be able to understand where this comes from and show me that you know where it comes from. Okay? So let's take a look at the features. It essentially tells us if the radius of the circle that the particle makes is going to be bigger or smaller, and what might be the reasons that that would happen. So first of all, it tells us that if the mass of the particle is bigger, the radius is bigger. In fact, they're directly proportional. So if you double the mass of the particle, what's going to happen to the radius? Double. R is proportional to m. Now, can we reason that conceptually? Yes, we can. If a particle has more mass, it has more inertia, right? It's more stubborn to make changes. Well, it's going to make more gradual turns. Right? That's why big trucks don't tend to make really tight turns, right? Okay? So more inertia means more gradual turns, larger radius turns. So, what about the other factors? Let's take a look at Q. If you increase Q, what happens to the radius? Increases, decreases?
Decreases.
Decreases. In fact, they're inversely proportional, right? So if you double the charge, you'll have the radius. So why is that? Well, if you double the charge, it makes, or if you increase the charge, it makes the magnetic field strong, or the magnetic force stronger, right? If you have a more violent force hugging the turn, it's going to hug it into a tighter turn, right? So this increases the magnetic force that's responsible for pulling this thing into a turn. By the way, it's much the same with the magnetic field itself. If you increase that, that also brings the radius down, and it brings the radius down for the same reason. The magnetic force gets stronger. So you can increase the magnetic force either by putting more charge on the particle, which of course means that it'll be more affected by the magnetic field you have, or you can make the field itself stronger, and that'll pull harder on any particle, right? So, the final factor is the weird one. I'm writing really crooked. I guess let me move over here. So this tells us that if we increase the speed, then what happens to the radius?
It also gets larger.
It gets larger.
Why is that weird?
So you would think that if you increased the speed, well, we just said if you increase the charge, and we increase the field, that makes the magnetic field stronger and hugs it into a tighter turn. And yet here we have that you go faster, which makes the magnetic force stronger, and it goes into a bigger turn, not a tighter turn, right? So what's up with that? Well, the problem is this. You have a V here, and you have a V here that's squared. So for instance, if you double the speed, you will make the magnetic force twice as strong. But here's the problem. How much more force do you need? How much more, what is this, how is the centripetal force?
Quadruples.
So if you go twice as fast, what happens to this side? 4 times. So you get twice the force, but you need 4 times the force to hold this turn. Well, guess what? Sometimes you don't get what you need, okay? So yes, the force does increase, but not as much as it needs to. Therefore, you do still fly out into a bigger circle. So paradoxically, if something goes faster, it simultaneously has more force acting on it and it flies out. Because yes, you need more force, but you get more force if you go faster, but it doesn't keep up with the voracious need of centripetal force because that increases as v squared, okay? So, there we have it. That's an important formula, and it's important to understand the features of it. R equals mv over qb. Make sure you know how to get that. It's certainly worth spending a couple bits of your memory to remember the results so that you have a sort of head check on setting fb equal to fc. The one line of algebra it takes to get this, maybe you'll make a mistake, you want to have some sort of guard against that, okay? So, with this, it's a good time to start making ourselves a little master chart of all the things that can happen with a particle if it gets thrown into a magnetic field, okay? So let me do that. So these are possible trajectories. If we make ourselves a catalog of all the different things that can happen, then we can't get surprised later. So, first, let me go ahead and just ask, is V parallel? Do you have a V parallel? Do you have a V perpendicular? And what is the details of the motion? Okay. So let's start with the simplest cases. You don't have either one of these. So you don't have any velocity components at all. So what are you doing?
Sitting still.
That's right. The particle just stays at rest. We talked about that last time. If you put a charged particle at rest in a magnetic field, it'll stay at rest. Okay? Remember, we just discovered that, or pointed out, that the magnetic force cannot change the speed. So if you don't have any speed to begin with, there's nothing to work with. You can't guide this thing onto another path if it's not doing anything. Okay? So magnetic field can't do work, and it can't increase the kinetic energy, so if you have none to begin with, you just get to sit there. Okay? How about if we have a V parallel, but no V perpendicular? So that means that it does move, but it moves either with or against the field line. And what is this subsequent trajectory going to look like? We talked about this last time as well. Just going to have a constant speed with or against the field line. That's right, constant speed a straight line, and this can be with or against the field line, which is of course all you can do. If you have no V perpendicular, that's how your motion started, and that's how your motion will continue. All right, so now, of course, the problem is that
That's okay.
the question of whether or not you have V perpendicular is a proxy for whether or not you have a force at all. So in those two cases, you had no V perpendicular, so you had no force. So really, it's just this past case that we just did that is the first case where we have V perpendicular, and therefore we have a force. But we also did not yet have a V parallel. Remember, we set this equal to 90 degrees right here. So this particular motion here was V, the entire thing is V perpendicular. V parallel is equal to nothing. We don't have one.
So just circle.
That's right. So that's a circular motion. So we learned the details of that. It's a circular motion with a radius of mv over qv. So from here, the final case should be left, or should be hopefully obvious. We need to let there be motion in both directions. In general, of course, you're entitled to throw a particle into a magnetic field however you feel like it. And in general, the velocity that you throw it with will have both components parallel and perpendicular to the field. Well, this is just a combination of the previous two lines. Okay? So what we will have is circular motion and a constant speed. Both. So how does that happen? Well, this component gives you your circular motion, and this component just gives you your field line drift. Okay? So, this is a bit tricky. Let me caution you. What does this look like? So that would be like a case like one of these two. So you once again set FB equal to FC. Here, we of course recognize, and here I'll use the shorthand, that it's only V perpendicular that gets involved in the magnetic force. And then, for the first time probably ever in physics 1 or 2, you have to be really, really, really careful with this. Because this is no longer the entire speed, okay? This is only V perpendicular. Let me explain. If you have a particle flying around in 3D space, there are generally 3 components, not 2, but 3 components to the velocity. And of these, let's say this situation right here, only 2 of them are involved in the circle. So these 2 might be combined into this, and this has nothing to do with it. Okay? So this here could be V perpendicular only. So this is just the component that's relevant. Okay? So every instance of you doing a circle previously, when you're going around and around, whatever that velocity vector that was going around was the entire velocity. Now there's a third component that has nothing to do with this. Okay? So there could be a component that goes into the page with the magnetic field, or against it, like this. Okay? Does that make sense? So, we only can count V perpendicular for this, so be really careful. This is now not the entire speed. Only 2 out of the 3 components are relevant to the circle. by the way, what happens if we're making this circle that I just have drawn here, but there's also a drift forward? What does the path look like?
Spiral.
Spiral or a helix. And remember that it can spiral either way. There could be a V parallel that goes with or against the field. So for instance over here, we would have a V parallel that's downstream. So this thing,
Thank you, bro.
you can see it's initially forces inward. It would spiral into the page first, and then it would go around like that. Okay? This one, it happens to have a V parallel that's against the field line, so it would spiral like this. Okay? It can spiral either way, right? It can spiral like this, or it can spiral like this, but it can't go around like this, right? The magnetic force sets the way that it circles, but then it can drift downstream or upstream, okay? So, what does the equation end up looking like? This is a helix, and if you solve, you get this. It's the same exact formula as before, except for, of course, the perpendicular is the only relevant thing. Now, if you had a hard time with this discussion, it's not something to worry about too much. The only thing you have to remember is that this is, don't try to solve this for yourself and forget that this is V and think that this is V in and of itself. You'll actually get the wrong equation here, okay? You'll get a sine theta in the denominator instead of in the numerator, okay? The drift, I'll just use good old distance equals rate times time, okay? That's the part that experiences no force. I guess I should have said that up here even. So over here, when that was the entire velocity, I could have just used the distance equals rate times time. Now, I'm combining the behavior from those two rows. So basically, V parallel goes in here, and V perpendicular goes in here. Okay?
So, Professor,
Yeah.
particles going in a circle, we just give it a push, and that's the x component is just gonna stay like that because it's V parallel, right? It's gonna stay like that for the whole movement.
Right, so if we throw it in like this, with no component downstream or upstream, it's just going to make a circle. Yeah. Is that what you're asking?
No, I'm saying like it's in a circle, and then we just give it a push to in front V parallel, and
Okay.
that's the x component is gonna stay the same all throughout the magnetic field.
Oh, I
right?
get it. So you're just calling that X component.
Yeah, exactly. Oh, yeah.
It can be any Y or
Any
Z,
Y,
but
yeah.
the point is that, yeah, if you give it a push parallel to the field, either with or against it, it'll just spiral in the direction that you pushed it. And
Exactly.
that new velocity component that you gave it with or against the field is going to stay constant. Question?
So delta x is a change in direction, how do you change that?
Yeah, oh, I see where Omar's confusion was. I was calling this delta x like generically, like, because I don't know, I just could call it V if I wanted, maybe that'd be better. But, you know, it's just the displacement with the field.
Okay.
So maybe that'd be a better way to do it. That's just V parallel or something.
Okay.
That's good. Perhaps if that's more informative than.
It's like in calculus we take y, x, and z. So z is the force for us.
Yeah,
so-
well, in physics we abuse which is x, y, and z all the time, so there's no universal standard.
Exactly.
Yeah. Does that answer your question? Okay. Okay, so that's the general motion of a particle. If you just at random throw a charge into a magnetic field, and it's more than likely not going to have any special relationship to the field, so it'll make a helix. Let me give you a bit of a demonstration that that's actually the case. So this is a fun little thing you can make at home. I have a battery. I have a wire so that I can connect and get some current. So obviously if I connect the current, I can get something to flow. I'm going to have the current go through this screw right here. So obviously if I send, if I put higher voltage on the bottom and lower voltage on the top, I can send it going up, or vice versa. If I put higher voltage on the top, then I can get it to flow down, right?
Mm-hmm.
So this thing happens to be made out of a magnetic material, so it will stick to this magnet, and this magnet will also supply a magnetic field. So the electrons, as they go through this this screw here, they will experience a magnetic
Spiral.
field, and they will spiral.
Mhm.
Okay.
Spiral.
So let's see what happens. Let me clean off the tip of this first. Okay. So I'll stick it to the bottom. That's another advantage of it being magnetized. It'll stick on the bottom. I'll send some current through there, and if I can get this to work, it doesn't keep on hitting my hand and going off track. It spins, right? Sorry, it's not that compelling.
The aerodynamics on the thing.
Gotta clean the end of that. Usually I can get it going pretty well. Wow. Sorry, that's very, very not exciting. Usually I can get it going very fast. Come on.
Are you touching it with a magnet or with the end of the nail?
I'm touching it on the magnet. Magnet's also a conductor, so it's
Oh,
just
okay.
smoother, so I don't get as much friction. Come on. This always works terribly and unpredictably. It was working great when I tried it. There we go.
There we go.
Oh,
It's the displacement of the yeah, it should be in the middle.
I think it's just going off track.
Uh-huh.
There we go. It's spinning. So
Yeah.
that's evidence. What's going on there is that instead of the electrons just going up and right through the nail, they're going through like this. They're spiraling as they go into the terminal. And of course, as electrons go through anything, they're going to bump into things, and that's why it takes the whole screw with them, right? It bumps into the fixed atoms that are in the screw, right?
That's a
So
lot
that
of
there we
force
have, just see with our own eyes, evidence that the charges, if subjected to a magnetic field, are going to spiral. Okay? This is something you can build yourself pretty easily at home. The only thing you need is a, basically a nail or screw. It doesn't matter. The threads are irrelevant. That has some magnetic material in it, so it'll stick to a magnet. And then you have to be able to hang it off here so that it's enough magnetization so it sticks and the magnet's not too heavy to just pull it off and grab it. It's something you can easily make yourself. The duct tape on the bottom is just so that people that aren't in the front row can see it spinning. Okay. The little duct tape propeller. Okay. So there's some evidence of the helical motion. The next order of business is that this force law that we just found, it's the gift that keeps on giving. We keep on building it up. So instead of just having one charged particle, we're going to have a bunch of charged particles in a wire. Then that wire that used to be straight, that wire will be turned into a loop. And each time we're just going to figure out what's the next law that we can build up from this. The next one is really easy. In fact, I have plenty of time to knock it out even in the few minutes we have left. So the next one is going to be the magnetic force on a current-carrying wire. The current will be I, and the length of the wire will be L. So let's do it. Let's say the magnetic field is, I don't know, into the page, and then we have a wire. Obviously, it has, it can't just start and stop, but I'm looking at this segment L. This is kind of a building block to making more complex things. But I just want to do a look at segment L. I have a bunch of charges that, of course, coursing down. That's what current is. And in any given cross section here, I can call the amount of charge I have there Q. So that might consist of, a bunch of electrons there. And the force on that charge will look like that. And then the only thing I'm going to do is I'm going to say that the speed at which that charge moves, well, that's just, it covers a length, the length L and a time delta T. So this becomes L over delta T. And then all I do is I group the charge with the time instead, because charge per time is what? Current. ILB sine theta. And I'm pretty much done. The only thing I'm going to do here, so I can get out of the microscopic world, is to identify not the angle between the individual velocities, but of course, I know that current points the same way as the velocity. So, just like that, I'm done. I'll recap that briefly next time, and then we'll just see what we can do with it.